Modern vision language models are dazzling at describing a single photo. But the real world rarely comes as one image. You flip through a photo album, compare frames in a video, scan a stack of documents. So this paper asks a deceptively simple question. When you give these models many images at once, do they actually see all of them? The uncomfortable answer is mostly no. Here's the gap they're filling. Vision language models, LVLMS, are now sold as multi-image capable, and a few benchmarks test them. But nobody had really pinned down where they break and why. Existing tests mix too many factors together, so you can't tell if a failure is about reasoning, perception, or just too many pictures. Their solution is a controlled testbed called Mimic. The trick is control. Instead of scraping messy real questions, they procedurally build multi-image puzzles from MS Coco's clean object labels and boxes. That lets them dial exact knobs, how many images, how the answer is spread across them, how many distractors, how many concepts, with unambiguous ground truth answers. It's built from 4 clean tasks, shown here. Counting, how many zebras across these images. Listing, name every vehicle you can find. Odd one, which object appears in only one image. And common, which object appears in all of them. Each one targets a different slice of cross-image understanding. Now the diagnosis, and the first finding is a genuine surprise. As you add images, accuracy collapses. But is it the number of images, or just the longer token sequence? They tease these apart, and find that simply shrinking the vision token sequence with 1D pooling by 4 to 8 times actually improves accuracy. The problem isn't many images. It's long sequences. And it gets more damning. Performance actually peaks when the vision sequence is about the length of just 1 or 2 images. In other words, these multi-image models are quietly behaving like single-image models. They do best when you basically feed them 1 picture's worth of information. Deepest failure is aggregation. When the answer is spread across several images, say 4 zebras in 4 different photos, accuracy nosedives toward 0. The models don't integrate evidence across images. Instead, they take a shortcut. They latch onto 1 image or a tiny subset and ignore the rest. 2 more cracks. Distractors. Drop in a few irrelevant images and accuracy can crater, in one case from 75% down to 12. And multi-concept tracking. Ask the model to count several object types at once, and it falls apart. It just can't hold multiple concepts in mind across images simultaneously. Then they open the hood and look at attention. In the early layers, vision tokens do attend across images. But as you go deeper, that cross-image attention fades, and tokens increasingly attend only within their own image. The model starts collaborative, then retreats into looking at each picture in isolation. That's the mechanism behind the single-image behavior. So they don't just diagnose, they propose 2 complementary fixes, one for the data, one for the architecture. The data fix attacks the training bias. The attention fix attacks the broken mechanism directly. Both are simple, and together they work. The data fix reuses Mimic recipe. They procedurally compose single-image annotations from open images into rich, genuinely multi-image training examples, roughly 200,000 of them, with sequences up to 10 images. This deliberately forces the model to practice the thing it's bad at, reasoning across many images at once. The attention fix is the clever bit. Since cross-image attention is useful early, but turns harmful and noisy in deep layers, they apply layer-wise attention masking. In the deeper layers, they restrict vision tokens to attend only within their own image. Keep collaboration early and force clean focus late. They train it efficiently with LoRa. And they prove the placement matters. Mask the early layers and performance tanks, because that's exactly where the model needs to gather evidence across images. Mask only the deeper layers, 12 through 23, and it works best. Early layers aggregate, deep layers should focus. The fix respects that division of labor. The payoff is big. On their own Mimic benchmark, the 500 million model's average jumps from 26 to 49. On the standard Mir bench, the 7 billion model leaps from 42 to 51, a new state of the art. And the gains hold across 6 different multi-image benchmarks. You can literally see the fix working. Here's a counting example. The baseline top row never attends to the potted plant in the 3rd image, so it answers 2. Their model bottom row lights up right on that plant and answers 3 correctly. The repaired attention is visible. And there's a bonus. The attention masking isn't just more accurate, it's cheaper. Because deep layers stop computing all those cross-image interactions, the masked model cuts compute by around 81% on the small backbone, while still beating full fine-tuning. Better and lighter at the same time. Why does this matter? Because so much real-world vision is multi-image: video frames, document pages, before and after photos, product galleries. This paper shows today's models quietly cheat by looking at one image, gives a precise diagnosis of why, and a practical, efficient fix. It's a roadmap for making vision models actually look at everything you show them. The authors are careful about scope. Mimic is built on MS Coco for tight control, so extending it to dense documents or medical scans is future work. Shrinking sequences helps semantic tasks, but jobs needing pixel-perfect tiny details might want adaptive resolution instead. And their analysis focuses on open-weight models. Closed ones are assumed similar but untested. So here's the one-line takeaway. Today's vision language models pretend to read many images but really lean on one, because deep layer attention abandons cross-image reasoning. Feed them targeted multi-image practice and mask attention to stay focused late, and they finally start seeing the whole album. Thanks for watching.